Welcome to this problem walkthrough. Today, we'll be tackling the problem titled Maximum Compatibility Score Sum. In this problem, we'll explore how to pair students with mentors to maximize compatibility scores. Let's dive in. In this problem, we are tasked with matching students and mentors based on their binary answers to a set of questions. Each student and mentor has their answers represented as a binary array, where a value of 1 means the answer is correct, and a value of 0 means the answer is incorrect. The goal is to pair each student with exactly one mentor in such a way that the total compatibility score is maximized. Now, the compatibility score between a student and a mentor is simply the number of positions where their answers match. For example, if both have the same answer at the first and third positions, those contribute to the compatibility score. The input will consist of two 2D arrays, one for the students and one for the mentors. Each row in these arrays represents the binary answers of an individual student or mentor. The output will be a single integer indicating the highest possible sum of compatibility scores achievable by pairing students with mentors optimally. Let's look at the first example. Here, we have 2 students and 2 mentors, and their answers are provided as binary arrays. For the pairing, student 0 is matched with mentor 0, and their compatibility score is 2. This is because their answers match at the first and second positions. Student 1 is paired with mentor 1, but their answers do not match at any position, so the compatibility score is 0. Adding these together gives a total compatibility score of 2. The task is to determine the optimal pairing to achieve this maximum score. Now, in the second example, we have 3 students and 3 mentors. Here, the optimal pairing is as follows: student 0 is matched with mentor 1, yielding a compatibility score of 2. Student 1 is paired with mentor 0, also resulting in a score of 2. Finally, student 2 is paired with mentor 2, but their answers don't match at any position, so the compatibility score is 0. Summing these values gives a total compatibility score of 4. This demonstrates how the pairing strategy can vary depending on the input, and finding the optimal pairs is key to maximizing the score. In the third example, we again have 2 students and 2 mentors. Pairing student 0 with mentor 1 yields a compatibility score of 3, which is the maximum possible score for this pairing because their answers match at all 3 positions. Student 1 is paired with mentor 0, but their answers don't match at any position, resulting in a compatibility score of 0. Adding these scores together gives a total compatibility score of 3. This example shows the importance of carefully evaluating all possible pairings to find the one that yields the best result. To summarize the constraints and edge cases, the number of students always equals the number of mentors, and there can be up to 8 students or mentors, with up to 10 questions in their binary arrays. The answers in the arrays are restricted to either 0 or 1. For edge cases, consider scenarios like having the smallest possible input, where there's only 1 student and 1 mentor. Here, the compatibility score depends entirely on whether their answers match. Another case is when there's no compatibility at all, leading to a score of 0. Conversely, in cases where all answers match perfectly, the maximum score is achieved by simply pairing each student with their identical mentor. Finally, some inputs might allow multiple valid pairings that achieve the same maximum score, which adds another layer of complexity to the problem. To tackle this problem, we start by analyzing its requirements. The goal is to maximize the total compatibility score by matching students to mentors. Compatibility is calculated as the count of matching answers in their respective binary arrays. Since the number of students equals the number of mentors, each needs to be matched exactly once. This is a combinatorial optimization problem, meaning we need to explore various possible matchings to find the one that yields the highest score. One straightforward way to approach this is by using a brute force method. Here, we generate all possible permutations of mentor assignments to students. For each permutation, we calculate the total compatibility score by summing the scores for each assigned pair. Finally, we return the maximum score from all permutations. While this guarantees the optimal solution, it can become computationally intensive as the number of students and mentors increases. Now, let's analyze the complexity of the brute force approach. Generating all permutations of mentor assignments involves factorial time complexity, O, n, because there are n. Ways to assign n mentors to n students. For each permutation, computing the compatibility score involves comparing n pairs, with each comparison taking O(n) time, leading to a total of O(n) squared per permutation. Combining these, the overall complexity becomes O(n) n squared. While this method is simple to implement and guarantees the optimal solution, it becomes computationally prohibitive for larger values of n, such as when n exceeds 8, due to the rapid growth of factorials. To address this, we consider a backtracking approach, which incrementally explores possible assignments. In backtracking, we assign mentors to students one by one, ensuring that we don't reuse mentors already assigned in the current path. Additionally, we apply pruning to terminate paths early if their partial scores cannot exceed the current maximum. This significantly reduces redundant computations compared to brute force. The backtracking approach has its own trade-offs. On the positive side, it is faster than brute force because pruning eliminates unpromising paths, and it still guarantees the optimal solution. However, its worst-case time complexity remains O(n), as we still explore all possible matchings in the absence of effective pruning. The space complexity is O(n), which is required for the recursion stack. To further optimize, we move to a more sophisticated approach, dynamic programming combined with bit masking. Here, we represent the state of mentor assignments using a bit mask. For example, a bit mask like 111 indicates that all mentors are assigned, while 000 means none are assigned. The key is to define dp mask as the maximum compatibility score achievable for a given state of assigned mentors. For each student, we transition between states by assigning an available mentor, calculating the compatibility score, and updating the dp state. This ensures that we systematically explore all possibilities while avoiding redundant calculations. Dynamic programming with bit masking offers notable advantages. First, it significantly reduces complexity to O(n*2 to the power of n, as there are 2 to the power of n possible states for mentor assignments, with n transitions per state. The space complexity is also O(2 to the power of n, which is efficient given the problem constraints. The pros of this approach include its scalability and guaranteed optimality, even for larger inputs where brute force and backtracking become impractical. However, there are trade-offs. The implementation is more complex, requiring a solid understanding of both dynamic programming and bitmask manipulation. Despite this learning curve, the benefits far outweigh the drawbacks for larger problem sizes. By leveraging bitmasking, we minimize redundant computations and ensure that only necessary transitions between states are performed, resulting in significant time savings. Dynamic programming with bitmasking is the best strategy for this problem because it balances optimality, efficiency, and scalability. Unlike brute force or backtracking, it scales well for larger inputs, such as n equals 15, where other methods fail. It guarantees the optimal solution while keeping time and space complexity manageable. However, it does require a deeper understanding of bitmasking and dynamic programming transitions, which makes it slightly more challenging to implement. Overall, this approach is superior for real-world applications where efficiency is critical. While brute force and backtracking are viable for small inputs, they are not practical for larger values of n. By choosing the dp plus bitmasking method, we achieve a solution that is both robust and computationally efficient, making it the ideal choice for this problem. To solve the maximum compatibility score sum problem, we aim to pair m students with n mentors, or m equals n, in a way that maximizes the total compatibility score. The compatibility score between a student and a mentor is determined by the number of matching answers in their respective binary arrays. For example, if a student's answers are 1, 0, 1, and a mentor's answers are 1, 1, 0, the score is 1 because only the first answer matches. The first step in our algorithm is to define a compatibility function. This function computes the score by iterating through the binary arrays and counting the indices where the values match. The implementation operates in L, where L is the length of the arrays. Following this, we pre-compute the compatibility scores for all student-mentor pairs and store them in an MXN matrix. Each entry in this matrix represents the compatibility score between a specific student and mentor. This pre-computation step ensures we avoid redundant calculations later in the algorithm and has a time complexity of O(m*n*L). Pre-computing the compatibility scores gives us a foundational matrix to work with, and the next step is to model the problem as an assignment problem. In this scenario, we can think of students and mentors as nodes in two separate partitions of a bipartite graph. The edges connecting these nodes represent the compatibility scores we calculated earlier. Our goal is to find the maximum weight matching in this graph, which means selecting the edges that maximize the total compatibility score while ensuring each student is assigned to exactly one mentor. To solve this, we use the Hungarian algorithm, also known as the Kuhn-Munkers algorithm, which is designed for finding the optimal assignment in such bipartite graphs. The algorithm begins by initializing two label arrays, Lx and Ly. The Lx array stores the maximum compatibility score for each student, while Ly is initialized to 0 for all mentors. This initialization sets the stage for iterative improvements. During the matching process, we use alternating paths to find and augment matches, ensuring that we assign each student to a mentor in a way that maximizes the total score. A slack array is maintained to track the smallest adjustment needed to improve the current matching. The Hungarian algorithm continues by adjusting the label arrays Lx and Ly based on the current slack values, ensuring that the matching remains feasible and optimal. This adjustment phase is key to maintaining the algorithm's efficiency and moving closer to the optimal solution. The process of finding alternating paths, updating labels, and adjusting the slack array is repeated iteratively until all students are matched to mentors. Once the matching is complete, we compute the final matching score by summing the compatibility scores of the selected student-mentor pairs. The Hungarian algorithm operates with a time complexity of O(n cubed), which is efficient given the problem constraints where n is at most 100. To implement this solution effectively, we rely on several key data structures. The scores matrix, a 2D array, stores pre-computed compatibility scores and avoids redundant calculations. The label arrays Lx and Ly manage weights for students and mentors. The slack array helps track the minimum adjustments needed during the label update process, and a matching array keeps track of the current mentor assigned to each student. Together, these components enable the algorithm to find the optimal solution efficiently. There are several insights that make this approach robust and efficient. First, by reducing the problem to a bipartite matching problem, we can leverage the well-established Hungarian algorithm to guarantee an optimal solution. Pre-computing the compatibility scores simplifies the process and avoids recalculating scores repeatedly, saving computational effort. The Hungarian algorithm itself, with its O(n cubed) complexity, is well suited for the problem size, as n is constrained to a maximum of 100. This ensures the solution is computationally feasible even for the largest inputs. Additionally, the algorithm handles various edge cases effectively. For instance, if all compatibility scores are 0, the algorithm still returns a valid matching, but the total score will be 0. If students and mentors have identical binary arrays, the algorithm naturally pairs them to achieve the maximum score. Finally, for large values of n, such as n equals 100, the cubic complexity remains manageable, demonstrating the scalability of the solution. Overall, the combination of pre-computing, efficient modeling, and the Hungarian algorithm ensures that our approach is both optimal and practical. Let's look at an example to bring everything together. Consider two students with answers 1, 0, 1, 0, 1, 0, and two mentors with answers 1, 1, 0, 0, 1, 0. First, we compute the compatibility scores for all pairs. For student 0 and mentor 0, the score is 1 because their arrays match at only one index. For student 0 and mentor 1, the score is also 1. For student 1 and mentor 0, there are no matches, so the score is 0. For student 1 and mentor 1, all three indices match, giving a score of 3. This results in the scores matrix 1, 1, 0, 3. Next, we apply the Hungarian algorithm to find the optimal matching. In this case, the algorithm assigns student 0 to mentor 0 and student 1 to mentor 1. The total score for this matching is 1 plus 3 equals 4. Therefore, the output of the algorithm is 4, which is the maximum compatibility score sum for this input. This code solves the LeetCode problem number 1947 maximum compatibility score sum using a brute force approach with permutations. The goal is to maximize the total compatibility score by pairing students with mentors optimally. First, the compatibility function calculates the compatibility score between a student and a mentor by counting the number of matching answers in their binary arrays. This is done using the zip function and a generator expression to compare corresponding elements. Next, the number of students, or mentors, is determined using len students, as the problem guarantees that the number of students equals the number of mentors. The scores matrix is pre-computed to store the compatibility scores for all possible student-mentor pairs. This is achieved by iterating over all students and mentors and calling the compatibility function for each pair. This pre-processing step ensures that we don't recompute scores during the permutation checks. To find the maximum compatibility score sum, the code iterates through all permutations of mentor assignments to students using the permutations function from the itertools module. For each permutation, the current underscore score is calculated by summing the compatibility scores for the assigned student-mentor pairs. If the current underscore score exceeds the max underscore score seen so far, max underscore score is updated. Finally, the maximum compatibility score found during the permutation checks is returned as the result. This approach is straightforward but computationally expensive, with a time complexity of O(n). *n, where n is the number of students or mentors. While this is acceptable for small inputs, it may not scale efficiently for larger values of n. Optimized approaches, e.g., dynamic programming or bit masking, would be more suitable for larger constraints. Here, we start with the Java implementation of the solution by importing the necessary utilities and defining the solution class. The key method, maxCompatibilitySum, takes two 2D arrays as input, one representing students and the other representing mentors. The first step is to calculate the compatibility scores for every possible student-mentor pair. This is achieved using a nested loop, where we iterate through all students and mentors and store the scores in a 2D array called scores. Each score is determined by a helper method, calculateCompatibility, which we will explore shortly. Next, we prepare to evaluate all possible mentor assignments by generating permutations. To do this, we use a helper method called generatePermutations, which creates all possible assignments of mentors to students. Finally, we calculate the maximum compatibility score sum by iterating through each permutation. For every assignment, the compatibility of each student-mentor pair is summed, and the maximum score is updated accordingly. Once the maximum score is determined, it's returned as the result of the maxCompatibilitySum method. Now, the calculateCompatibility helper method is designed to compute the compatibility score between a specific student and mentor. This is done by iterating through their attributes and simply counting how many of them match. A higher count means a better compatibility score. Additionally, the generatePermutations method is responsible for creating all possible arrangements of mentor indices. It uses backtracking to explore every combination, adding valid permutations to the result list. For each potential assignment, we ensure that no mentor is reused by keeping track of which indices are already used with a Boolean array. When a valid permutation is found, it's added to the list, and the function backtracks to explore other possibilities. The generatePermutations method concludes by ensuring all possible mentor assignments are accounted for. This guarantees that the maximum compatibility score is derived from evaluating every possible pairing of students and mentors. With these helper methods in place, the program efficiently calculates the maximum compatibility score sum by combining the pre-computed scores with the permutations of assignments. This modular approach ensures clarity and maintains the integrity of the solution. To solve this problem, we start by defining the compatibility function, which measures how well a student and a mentor match based on their answers. The score is calculated by summing the number of answers where both the student and mentor agree. For example, if we compare student 1, 1, 0 with mentor 1, 0, 1, their compatibility score is 1 because they only agree on the first answer. On the other hand, student 1, 0, 1 and mentor 1, 0, 1 have a perfect score of 3 because all their answers match. Once we have this function, we pre-compute the compatibility scores for all possible student-mentor pairs and store them in a matrix. For our example, the matrix looks like this: 1, 2, 3, 1, where each entry represents the compatibility score between a specific student and mentor. Next, we generate all possible mentor assignments using permutations. For our 2 students and 2 mentors, there are 2 possible assignments: assigning student 0 to mentor 0 and student 1 to mentor 1, or swapping the assignments. These permutations will help us evaluate all potential pairings efficiently. Now that we have the permutations, we calculate the total compatibility score for each assignment. For the first permutation, where student 0 is paired with mentor 0 and student 1 with mentor 1, the scores are 1 and 1 respectively, leading to a total of 2. For the second permutation, where student 0 is paired with mentor 1 and student 1 with mentor 0, the scores are 2 and 3 respectively, giving a total of 5. Among these, the highest score is 5, which becomes our result for this example. Moving on to a new example, we have students 0, 0, 1, 1, 1, 1, and mentors 1, 1, 1, 0, 0, 1. First, we calculate the compatibility scores for all pairs. The resulting scores matrix is 1, 3, 3, 0, where, for instance, student 0 has a score of 1 with mentor 0 and 3 with mentor 1. With the scores matrix prepared, we again consider all possible mentor assignments. For this example with 2 students and 2 mentors, the permutations are the same: 0, 1, and 1, 0. For the first permutation, where student 0 is paired with mentor 0 and student 1 with mentor 1, the scores are 1 and 0, resulting in a total score of 1. For the second permutation, with student 0 paired with mentor 1 and student 1 with mentor 0, the scores are 3 and 3, resulting in a total score of 6. Therefore, the maximum compatibility score for this example is 6. Let's analyze another example to solidify the concept. This time, we have students 1, 0, 0, 1, and mentors 0, 1, 1, 0. For this new example, we start by calculating the compatibility scores for all pairs of students and mentors. The resulting scores matrix is 0, 2, 2, 0. This score distribution indicates that each student is perfectly compatible with one mentor and completely incompatible with the other. As before, we generate all possible mentor assignments, which are 0, 1, and 1, 0. For the first permutation, where student 0 is paired with mentor 0 and student 1 with mentor 1, the scores are 0 and 0, giving a total score of 0. For the second permutation, where student 0 is paired with mentor 1 and student 1 with mentor 0, the scores are 2 and 2, resulting in a total score of 4. From the scores calculated for each permutation, the highest total compatibility score is 4. This is the optimal result for this example. By following the same steps, calculating the compatibility scores, generating mentor permutations, and evaluating the total scores for each, we can systematically find the maximum compatibility score for any given students and mentors. This process ensures that we consider all possible assignments to achieve the best possible outcome. To analyze the time complexity of the algorithm, we start by breaking it into 3 main steps. First, the compatibility scores are pre-computed for every student-mentor pair. This involves comparing the answers of a student with those of a mentor, which takes m time per pair, where m is the number of answers. Since there are n students and n mentors, the total time required to compute the compatibility scores for all pairs is n squared asterisk m. Next, we generate all possible permutations of mentor assignments using the permutations function from the Python library. Since there are n mentors, the number of permutations is n factorial, or n. Finally, for each permutation, the algorithm calculates the total compatibility score by summing the scores for the assigned student-mentor pairs. This involves summing up n values for each permutation, which takes n time per permutation. Given that there are n permutations, the total time for this step is n asterisk n. Thus, these 3 steps together form the basis of the time complexity analysis. Now, combining the time complexities of these steps gives us the overall time complexity. Pre-computing the compatibility scores takes n squared asterisk m. Generating all possible permutations and evaluating their scores takes n asterisk n. The dominant term here is n asterisk n, which means the overall time complexity is n asterisk n plus n squared times m. Since factorial growth is much faster than the quadratic term, especially for larger values of n, the pre-computing step becomes negligible in comparison. Therefore, the time complexity simplifies to O(n)(n), which dominates the performance for large N. This reflects the computationally intensive nature of the algorithm when the number of students and mentors increases. Next, let's examine the space complexity. The primary space requirement comes from the compatibility scores matrix, which stores the scores for all student-mentor pairs. Since there are n students and n mentors, the matrix has n rows and n columns, requiring O(n)² space. The permutations function, on the other hand, generates permutations on the fly without storing all of them in memory. However, generating each permutation temporarily requires O(n) space. Apart from these, the algorithm uses a few additional variables like max_score, perm, and current_score, which take constant space, or O(1). When we combine these, the space complexity is dominated by the compatibility scores matrix, leading to an overall space complexity of O(n)². This makes the algorithm efficient in terms of space usage relative to its time complexity. Finally, let's compare the brute force approach used here with potential optimizations. The current solution evaluates all possible assignments, making it a brute force method. While pre-computing the compatibility scores reduces redundant calculations, there is no optimization to reduce the number of permutations evaluated. A more efficient approach could use dynamic programming or backtracking with pruning to eliminate invalid or suboptimal permutations early. Regarding the best, average, and worst cases, the time complexity remains O(n)(n) in all scenarios since every permutation is evaluated regardless of the input. Mathematically, generating permutations of n items takes O(n), and summing compatibility scores for each permutation requires O(n). These two components multiply, resulting in O(n). Pre-computing the compatibility scores, which is O(n)²(m), is a lower order term and does not affect the dominant complexity. In summary, while the algorithm is space efficient with O(n)² usage, it is computationally expensive for large N due to its factorial growth in time complexity. There are a few common mistakes you should watch out for when solving this problem. First, one common error is using a greedy approach where students are assigned to mentors based purely on the highest immediate compatibility score. The issue here is that this method doesn't account for the global impact on the remaining pairs, which can leave you with highly incompatible pairs later, leading to a suboptimal solution. Another mistake is ignoring the permutations of assignments. Some might assume the order of students and mentors doesn't matter or fail to explore all possible pairings. Since the goal is to maximize the global score, you must consider all permutations to ensure the best outcome. Lastly, failing to pre-compute compatibility scores is a frequent oversight. Recomputing these scores during the algorithm not only increases time complexity but also introduces redundancy. Pre-computing and storing the scores in a matrix is a much more efficient approach. Another common pitfall is incorrectly implementing backtracking or bitmask DP. For example, you might forget to track visited states properly in backtracking or miss important base cases in dynamic programming. This can lead to incorrect results or even infinite recursion loops. Additionally, some might assume that the number of students and mentors is always equal, but this isn't guaranteed by the problem statement. Writing code that only works when m equals n can cause failures when the input sizes are mismatched. Always ensure your solution handles such edge cases gracefully. When tackling this problem in an interview, there are a few insights to keep in mind. Recognizing the underlying pattern is crucial. This is a classic optimization problem involving permutations. A brute force approach, while simple, becomes computationally infeasible as the input size grows, so techniques like backtracking or bitmask DP are necessary. Pre-computing a compatibility matrix is another key insight, as it significantly reduces redundant calculations during the pairing process. When considering different approaches, remember that brute force guarantees correctness but is slow, backtracking is more efficient but requires careful pruning, and bitmask DP is the most optimal but demands a solid understanding of state representation. Lastly, don't overlook edge cases. Be ready to handle scenarios like empty inputs, one student with multiple mentors, or vice versa. If you want to deepen your understanding, exploring related problems can be very helpful. For instance, LeetCode 1387, which focuses on sorting integers by the power value, involves optimization and dynamic programming techniques. LeetCode 698, partition to k equals some subsets, emphasizes backtracking and state management. LeetCode 1723, find minimum time to finish all jobs, deals with optimization using backtracking and bitmask DP. Finally, LeetCode 526, beautiful arrangement, is another problem that involves permutations and backtracking to maximize a score. Studying these problems will help you develop a better intuition for solving similar optimization challenges. There are several approaches to solving this problem, each with its own trade-offs. The brute force method involves trying all possible student-mentor pairings and calculating the total compatibility scores. While it guarantees correctness, its complexity of n makes it impractical for larger inputs. A more efficient approach is backtracking with pruning, where you explore pairings but prune branches when the score is already suboptimal. This reduces the effective search space significantly, though the worst-case complexity remains n. The most optimal approach is bitmask DP, where you use a bitmask to represent mentor availability and solve the problem with dynamic programming. This has a complexity of n*2 to the power of n, making it the fastest solution for larger inputs, but it also requires a deep understanding of state management and debugging. Another possible approach is greedy matching, where you iteratively assign students to mentors based on the highest compatibility score at each step. This method has a complexity of n², making it fast and easy to implement. However, it doesn't guarantee the maximum score because it overlooks the global impact of each assignment. While this approach might work well for smaller cases or as a quick heuristic, it's not suitable when the goal is to achieve the optimal solution. Great work on making it through this problem. We've summarized the key points, including the algorithm used, complexity considerations, and important takeaways. Keep practicing similar backtracking problems to strengthen your skills. Thanks for watching, and we hope to see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!